Dear colleagues, by means of this video, we want to learn how to estimate the dimension of a heat exchanger. The heat exchangers are mainly of two categories, the shell pipe and the plate frame. The plate frame are mostly on the shelf products, while the others are customized. And here we concentrate on the last ones and try to understand which physical parameters are affecting the choice, let's say the geometry, even though the complete selection should be made by suppliers themselves. Let's start and see together. The heat exchangers are used to transfer heat from a medium to another, and since a heat transfer is taking place, one is getting colder and the other hotter. This is the cooling one and this is the heating medium. And here is represented a chart with the corresponding temperatures. And the medium can be either a liquid, a vapor, or a gas. Any combination is possible. About the construction, there can be pipes, round, elliptical, or square, with or without fins. They have always 4 gates, 2 for each medium, inlet and outlet. There are two types of heat exchangers, the plate and frame and the shell and tubes. The plate exchanger is made by steel plates sealed each other by gaskets. Here are the plates and in between there are gaskets. As you can see in the picture, the plates are flown alternatively by the fluid 1 and by the fluid 2 in order to form two separate channel systems in counterflow. So the media cannot be mixed. They are very compact and extensible. Their selection can be done by dedicated tools provided by vendors. We can resume here the advantages. They are compact, they can be extended by adding new plates, the cost is generally lower than other type of exchangers, and there are existing preset calculation tools. The shell pipe exchangers are made of pipes instead. They have no gaskets, so they can stand higher pressure and temperature, and they are suitable for any type of fluid, and they are less sensitive to dirtiness. On the other hand, they are something bulkier and more expensive. We can resume here the advantages. The best use is for phase change. They can stand high pressure and temperature because of no gaskets. They have low pressure drops compared with the plate ones, and they can be customized, so the size can be chosen practically freely from the customer. They can stand dirtiness, the cleaning is easier, and they can deal with any type of fluid or gas. In our presentation, we take care only of them, since they are the ones suitable for any application. And moreover, because it's difficult to find the tools from manufacturers to size them. Here we want to find a method for answering two questions. Should I need a new exchanger? What is the size? Number one. I have an existing exchanger that I have to use elsewhere. Does it fit? Second question. Let's start from the physical laws. We have two fluids. One is the process fluid and the other the service fluid. We assume that our process fluid needs being cooled and also it's flowing in the shell, while the service fluid in the pipes. This is our process fluid, which needs to be cooled, and this is our service fluid, which is getting hot. We call T1 the temperatures at the left side of the exchanger and T2 the ones at the right, so we can represent a chart of the temperatures evolution of the two fluids. Those are the T1s on this side and those are the T2 on that side. Both temperatures of the process are known, so T1P and T2P are known. Moreover, the entry temperature of the service fluid T2S is known. We have three equations at disposal. The first equation says that the heat lost by the process is equal to the product of the heat capacity, Cp, the mass flow, Mp, and the delta T, T1P minus T2P, this difference. This is the difference between the entry and leaving condition. By means of it, we can determine the value of Q, the heat flow, in kilowatt. The second is similar to the first and says that the heat gained by the service fluid is the product of the thermal capacity, delta T, and mass flow, which is different in this case, And since the heat loss from the first is gained by the second, the Q is the same. And now we can determine the leaving temperature of the service fluid, T1S. The third equation says that the heat transferred across the heat exchanger is also a product among three terms: the coefficient K, the heat transfer A, and the delta T mean. This delta T is different from above, is not any longer the difference between the entry and leaving of the same fluid, since here the fluids are two. Actually, it is the difference among the two fluids at the same position. This is a delta T across the heat exchanger. This temperature minus this. And since this temperature difference changes across the heat exchanger, we take an average. This is not an arithmetic mean, but a logarithmic one. We cannot explain here the reason for that. In any case, this is not much different from the arithmetic mean. From this equation, we can get the area of the exchanger. If we know K, in the next slide, we explain how to get the coefficient K. The determination of K is the most difficult part of the heat exchanger calculation. Now, the heat flows from the higher to the lower temperature, so in this case, from the process to the service fluid. And K is the transmittance. The higher is K, the more is the heat transferred for a given delta T. The inverse of K is called thermal resistance, here represented, and the thermal resistance of a heat exchanger is a series of three resistances: the resistance across the first fluid, in this case the process one, the resistance across the wall thickness of the pipe, and the resistance across the second fluid, the service one. The thermal resistance across a fluid is the inverse of the convection factor. The convection factor is expressed by this relation, where Nusselt is a dimensionless number, lambda is a conductivity, and d is the outer diameter of the heat exchanger, which we need to guess. Nusselt, on his part, is depending upon two other dimensionless numbers, Reynolds and Prandtl, and they are also depending upon the fluid property, its temperature, and the geometry, by means of this diameter and also by means of the velocity of the fluid itself. About the heat transfer across the pipe, we have only conduction, so the resistance is given only by the thickness S of the pipe and the material of the pipe or the heat exchanger itself. So it's quite easy to determine. Definitely, this K is not a constant for a given exchanger. It does depend upon the geometry and material, but also upon fluid type and its velocity. Let's start with an example. If we take the formulas already seen and apply them to a real case, we may clarify what we have seen. We assume that we have to cool water by using other water. Given are the inlet and outlet temperature of the process from 65 to 48 degrees and also its flow rate 100 cubic meter per hour. Given is also the flow rate and temperature of the cooling water, respectively 80 cubic meter per hour and 25 degrees. From the first equation, we get the heat power 1977 kilowatt. From the second one, we get the temperature of the living cooling water 46.3 degrees. By means of the four known temperatures, we get the mean delta T, which is 20.8 degrees. And using the third formula, we come to the value of K times A, which is 95 kilowatt per Celsius. Now it comes the most difficult part of the calculation. We need to take some assumption or guess values for the heat exchanger. The thickness of the inner pipes we can set at 2 millimeters. The speed of the process fluid, the fluid number 1, we put at 1.3 meter per second, and the speed of the service fluid at the double. Those speeds can be freely chosen. The higher is the speed, the higher will be the transfer coefficient K, but the pressure drops are also increasing, and therefore there are good practices per each fluid. In case of water, the speed must stay in the range between 1 and 4 meters per second. typically the water in the shell is also slower than the water in the tubes, and that is the reason for above choice. From the two speeds above, knowing the flow rates, respectively 100 and 80, we come to the cross area of the exchanger. So this area here, which must not be confused with the exchange area of the exchanger that we need to find now. And by knowing the cross area, we can determine the outer diameter, nearly 200 millimeters. Assuming stainless steel for the material of the exchanger, also lambda is known, and therefore we can determine the transfer coefficient K, 2756 watt over square meter per Celsius. By dividing the result of the previous page, 95 kilowatt, by the found K, we get the heat transfer area A, and by taking a safety margin of 10% against fouling, we come to 38 square meter. This is the exchange area of the exchanger, practically the sum of the outer area of each pipe within the exchanger. And this is our result. I hope you have enjoyed and you have learned something new that you can use in your daily life. And see you again. Stay healthy.